Hello students, hope you are doing well. Now we are going to discuss about deep learning. Deep learning has emerged as groundbreaking field within artificial intelligence, revolutionizing various domains and unlocking unprecedented capabilities in data analysis, computer vision, and natural language processing, and much more. In this comprehensive guide, we will delve into the world of deep learning, exploring the foundations, architectures, applications, and future prospects. From the basis of neural network to advanced techniques like convolution and recurrent neural networks, we will examine the key concepts, methodologies, and challenges associated with deep learning. So be with me on this interesting journey as we unravel the immense potential of deep learning and its transformative impact on the technological landscape. So now first go through the table of contents of this lecture. Introduction to deep learning, fundamentals of neural network, deep learning architectures, deep learning for computer vision, natural language processing with deep learning, deep reinforcement learning, challenges and ethical consideration in deep learning, advances in deep learning research, implementing deep learning tools and frameworks, and last we have future prospects and concluding our remarks. Deep learning, a subfield of machine learning, focus on creating neural networks with multiple layers, initiating them to learn complex patterns and representations from large datasets. This section provides a clear definition of deep learning and highlights its core principle, including the role of artificial neurons, activation functions, and the back propagation algorithms. Tracing the historical roots of deep learning, this subsection explores the contribution of key researchers and pivotal moments that shaped this field, from the initial ideas of artificial neural networks to breakthroughs in deep learning architecture. We examine the evolution and milestone of this rapidly advancing discipline. To understand the potential and scope of deep learning, it is essential to recognize its strengths and limitations as well. This section discusses the advantages such as ability to automatically extract features and its remarkable performance in various domains. Additionally, it addresses the challenges and limitations faced by deep learning, including the need for large amounts of labeled data and computational resources. What is fundamentals of neural network? First we have artificial neurons and activation functions. Neurons are the building blocks of neural networks. Here we explore the structure and function of artificial neurons, including the weighted sum of inputs, activation functions, and Bayes terms. We discuss popular activation functions like sigmoid, ReLU, and softmax and their implication in learning. Second, feedward neural networks. Feed-forward neural networks are the foundation of deep learning models. The subsection elucidates the structure of an operations of feed-forward networks, including the concepts of layer, forward propagation, and the role of weights and biases. We also delve into the universal approximation theorem and its significance in understanding the expressive power of neural networks. Third one we have back propagation and gradient descent. Back propagation is crucial algorithms for training neural networks. In this section, we unravel the mechanics of back propagation, explaining how it calculates the gradient of the loss function with respect to the network's parameters. We also discuss gradient descent optimized algorithms, including stochastic gradient descent known as SGD, ADAM, and RM-Seprot. Last one we have optimization techniques. Deep learning models require efficient optimization techniques to improve training speed and convergence. This subsection explores various optimization to techniques such as batch normalization, weight initialization strategies, learning rate schedules, and regularization methods like dropout and L1 L2 regularizations. Our next section is deep learning architectures. First one we have CNNs. Convolutional neural networks revolutionized computer vision tasks. Here we investigate the architecture of CNN, focus on conventional layers, filters, pooling operations, and the concept of respective fields. We discuss the impact of CNN in image classification, object detection, and other vision related to the same tasks. Next one we have RNNs. Recurrent neural networks excel in sequential data processing, making them invaluable in natural language processing and time series analysis. This section explores the architecture and components of RNN, including the vanishing gradient problem and solution like LSTM and GRU cells. We also discuss applications such as language modeling and machine translation as well. Third one we have GAN. Generative adversarial networks has revolutionized field of genetic modeling. This subsection provides an in-depth understanding of GNS principle, including the generator and discriminator networks, adversarial training, and the objective function. We explore applications such as image synthesis, style transfer, and anomaly detection, along with challenges like model collapse and training instability. Last one we have transformer. It is not much similar to the electrical transformer, as you know that in your streets or in your houses. Transformers have become the pivotal in neural language processing tasks, especially since the introduction of attention mechanism. We delve into the concept of attention, self-attention, and multi-head attention in transfer architecture. We explore the transformer model working principle and its application beyond language translation, such as text summarization and question answering systems. Our next section is deep learning for computer vision. First we have image classification and object detection, our fundamental task in computer vision. This section provides a detailed overview of the methodologies used in these tasks, including the preparation of datasets, the role of convolutional neural networks, and the advancement in region-based convolution neural networks (RNN), such as faster RCNN and masked RCNN. Second, we have image segmentation. Image segmentation aims to assign a label to each pixel in an image, enabling precise object localization. We explored semantic segmentation and instance segmentation, discussing popular approaches such as UNet, FCN, and masked RCNN. Applications in medical imaging, autonomous vehicles, and semantic understanding are highlighted. Last one we have object tracking and video analysis. Plays a vital role in the surveillance, robotics, and augmented reality. The subsections cover single object tracking techniques, including correlation filters and Kalman filters. It also dives into multiple objects tracking approaches such as sort and deep sort, which enable tracking in complex scenarios. Now we will discuss natural language process with deep learning. Word embedding and text representations. Word embedding from the foundation of language understanding in deep learning models. We explore popular techniques like word-to-wake, GLOVE, and FastAs, discussing how they capture semantic relations between words. Additionally, we examine methods for representing text, including bag of words and TF and 2ITF. Second, we have recurrent neural network for language modeling. Recurrent neural networks (RNN) has revolutionized language modeling. We explain how RNN can generate text and perform tasks like sentiment analysis and named entity recognition. We also delve into the challenges of long-term dependencies and explore advanced models like Gated recurrent units, GRUs, and LSTMs. Third one, we have sequence-to-sequence model are widely used for tasks such as machine translation, text summarization, and chatbots. This section delves into the architecture and training of encoder-decoder model, attention mechanisms, and beam search algorithms. We discuss popular models like Google Neural Machine Translation, GNMT, and the Transformer. Attention mechanism in NLP. Attention mechanisms have become a crucial component in NLP model, enhancing their ability to focus on relevant information. We explore different attention mechanisms, including self-attention and scale dot product attention. Applications like sentiment analysis, question answering, and language translation demonstrate the efficiency of attention-based model. Transformer-based language models. Transformers have revolutionized language modeling, culminating in models like GPT and BERT. The subsection dives into the architecture of transformer-based models, pre-training and fine-tuning processes, and the significance of masked language modeling and next sentence prediction tasks. We explore the impact of these models on various natural language processing benchmarks and downstream applications. Last one, we have language translation and sentiment analysis. Language translation and sentiment analysis are prominent NLP tasks. We examine the application of deep learning models in machine translation, discussing approaches such as encoder and decoder architecture, attention mechanism, and beam search. We also explore the sentiment analysis techniques, including sentiment classification and aspect-based sentiment analysis. Next, we have deep learning enforcement. Reinforcement learning, also known as RL, involves agents to interact with an environment to maximize a reward signal. The section provides an introduction to RL, discussing mark decision processes, MDPs, policy value function, and the exploitation trade-off. We introduce key RL algorithms, including Q-learning, Monte Carlo methods, and temporal difference TD learning. Deep Q networks DQN combine deep learning with enforcement learning to achieve impressive results in games like Atari and Go. We explored the DQN architecture, the reply buffer, target networks, and experience reply. We discussed extensions like double DQN, dueling DQN, and rainbow DQN, which address limitations and improve performance. Policy gradient models. Policy gradient models directly optimize the policy of an agent using gradient-based optimization technique. We delve into the policy gradient algorithms such as reinforced proximal policy optimization (PPO), also known as, and trust region policy optimization, short form TRPO. We discuss continuous control, task, actor critic methods, and challenges associated with policy optimization. Actor critic architectures. Actor critic architectures combines the strength of the value based and policy based methods. This explains the concepts of actor critic framework and its components, including the actor network, Arctic network, and advantage function. We explore popular algorithms like advantage arctic critic A2C and asynchronous advantage actor critic A3C. Do not complex with these terms. You don't need to memorize short terms or short form. You just memorize the full form, which is easy, and you can't be forget easily. Last one, we have applications in game playing and robotics. Deep in reinforcement learning has achieved remarkable success in game playing and robotic domains. We showcase the accomplishment of deep reinforcement learning algorithms in game in AlphaGo, Dota 2, and poker. We also explored the application of RL in robotics, including tasks such as manipulation, locomotion, and autonomous navigation. Now we discuss what are the challenges and ethical considerations in deep learning. Data bias and fairness. Deep learning models are susceptible to bias in training data, which can lead to unfair or discriminating outcomes. The section delves into the challenges of data bias, fairness metrics, and techniques like adversarial debiasing and causal modeling to address these issues. We explore the importance of diverse and representative datasets in training unbiased models. Privacy and security. Deep learning models often deal with sensitive data, raising concerns about privacy and security. It also discusses the privacy preserving techniques such as federated learning, secure multi-party computation, and differential privacy. We explored the adversarial attacks on deep learning models and defense mechanisms like adversarial training and input sanitization, explainability, and interpretability. Deep learning models are often criticized for being black boxes, lacking interpretability. We investigate techniques like feature visualization, silencing maps, and attention maps to provide insights into model predictions. We explore explainable AI approaches like line and shape values, which aim to bridge the gap between complex models and human understanding. Future of deep learning ethics. We pondered the ethical implication of deep learning and its future direction. We discussed the responsibilities of researchers, prac- sorry, practitioners, and policymakers in addressing bias, transparency, and accountability in deep learning application. We explored the need of interdisciplinary collaboration and the potential impact of regulation on deep learning ethics. Now there are some advancements in deep learning research, transfer learning, and few short learning. Transfer learning enables leveraging knowledge from pre-training to improve performance on new tasks. We discuss transfer learning techniques including feature extraction, fine-tuning, and domain adaptation. We also explore few shorts like approaches which aim to learn from a smart number of labeled examples such as meta-learning and metric learning. Some of the terms are not discussed right now, but it will be discussed in upcoming lectures, so don't need to worry about that. Meta learning and auto machine learning. Meta learning focus on training models that can quickly adapt to new tasks or environments. We delve into meta learning algorithms like ML and Reptile, which optimize for fast adoption. We also explored the emerging field of auto machine learning, which aims to automate the process of designing and optimizing deep learning architectures. Deep reinforcement learning breakthrough. Deep reinforcement learning continues to witness significant advancements. We explore recent breakthroughs such as AlphaGo and AlphaZero, OpenAlpha 2 bot, and DeepMind Muzero. We discussed the impact of these achievements on the field and the potential application and challenges they bring forth. Quantum computing and deep learning. Quantum computing holds promise in realizing deep learning. This subsection provides an overview of quantum computing principles, quantum neural networks, and quantum inspired optimization algorithms. We discuss the potential advantages of quantum deep learning and the challenges in harnessing the power of quantum computers. Implementing. Next, we have implementing deep learning tool and frameworks. We will discuss some of the importance, but there are much more. First, we have TensorFlow. TensorFlow, developed by Google, is a popular deep learning framework known for its flexibility and scalability. We explored TensorFlow's key features, including its computation graph, automatic differentiation, and the TensorFlow extended TFX ecosystem. There are examples and discuss of compatibility and hardware accelerators as well. PayTalk, developed by Facebook, has gained popularity for its dynamic computational graph and intuitive interface. We provide code examples and highlighted PayTalk intensive ecosystems of library and pre-trained models. Next, we have Keras. A high-level deep learning library provides a user-friendly API and support multiple backends, including TensorFlow and PyTorch. Code examples are demonstrate that ease of developing deep learning models with Keras. Last but not the least, we have Caffe. Is a deep learning framework known for its efficiency and suitability for conventional neural networks. Last one, we have Thano. A deep learning library focuses on optimizing mathematical expression for efficient computation. Code examples showcase Thano's functionality and its role in implementing deep learning models. Now we discuss some of the important future aspects and our conclusion remarks on deep learning. Deep learning in industry and society. The impact of deep learning in various industries, including healthcare, finance, transportation, and entertainment. We discuss how deep learning is driving innovation, improving efficiency, and transforming processes. We also explored the societal implications and potential challenges for widespread deep learning adoption. Second, we have research direction and emerging applications. We already discussed and explored the frontier of deep learning research, discussing emerging trends and promising direction. Topics such as supervised learning, graph neural networks, continual learning, and explainable AI are covered. We highlight potential applications in areas like robotics, healthcare, climate modeling, and quantum machine learning. I hope you guys understand all the concepts related to deep learning. If you have still any questions, feel free to ask me anytime. I will reply them in shortly. And one most important thing for all the students and learners, please follow my course outline and watch my videos in a progressive way, like first in a course outline as we discuss. So don't uh, visit my videos descending or mix up in category. First you see last video, then you have to see first video, then you have to go on move video. Please follow the course outline and continue this course in a sequence. Don't disturb it, otherwise you will not understand the important concepts related to the specific areas. So have a good day. See you in our next amazing lecture.